Okay, now that we've looked at several types of exponential equations, we want to look next to what we call logarithmic equations. Now, we used logarithms to solve exponential equations, but in a logarithmic equation, there's already a log to start with in the problem. Like in this example, we're trying to solve for x, and it's inside of this log base 3. So what we're going to have to do is get rid of the logarithm, and there's two ways to do that. They're really, by definition of the logarithm, they're equivalent to each other, but they're different ways of thinking about it. I used to always prefer, like in the rest of algebra, the whatever you do to one side you do to both approach. And in that approach, we can get rid of the log by using its inverse. So we take the base, which is 3 in this case, and we'll do 3 to this side equals 3 to this side. If you do that, 3 to the log base 3 will cancel out. So I believe that's the form I have. Actually, I did it by rewriting as an exponential. So you can do 3 to this side equals 3 to this side, and you'll get the inside equals 3 squared. So if you like, whatever you do to one side, do to both. Over the years, I think I've finally decided it's a lot quicker just to rewrite the log as an exponential. If you can remember the definition of logarithm, you take the base raised to this number equals the inside. So 3 squared equals x squared minus 6. So again, two ways of arriving at that equation. Doesn't matter to me which you use, as long as you pick one and you understand it. They're both equivalent to the definition of logarithm, being the inverse of the exponential. But you could, a quick way is just to take the base. 3 to this side wipes it out, equals 3 to this side. So if I do 3 to this side, I get x squared minus 6 equals 3 squared. But if you want to kind of skip one step, 3 squared equals the inside by rewriting it as an exponential. And then you just solve that equation. This one's pretty simple. You can isolate x squared, add 6 to both sides. Square the 3, add 6, you get 15. Take the square root, you get x is plus or minus square root of 15. Now in the guidelines on the next slide, I'm going to mention you need to check for extraneous solutions. As far as I can tell, of all the examples I've ever looked at and thought about this, if you start with a single log, you're not going to create an extraneous solution. But when you combine logarithms together, you often do, as we'll see in an example in a second. But here, both of these solutions work. What you have to worry about is when you plug the number in, is it in the domain of the expression here? And because of the x squared, both of these, whether it's positive or negative, when we square it, we'll get a positive and it works just fine. Okay. But so our general guidelines, again, just like I did with exponentials, we started with one that was already isolated and we can kind of jump to step 2 on it. But sometimes you have to do a little bit of algebra first, and you want to isolate this single logarithm equals a number on the other side and then get rid of the logarithm. Sometimes you have to combine logarithms. We're going to do an example in a second where we have to use our rules to combine logarithms. That's when you have to really look out for creating an extraneous solution as well. But once you get it down to a problem like we just had, again, there's two ways to think about it. You either raise the base to each side of the equation. B to the log base b of this side equals b to whatever's on the other side, and that'll get rid of the logarithm. Or you can do the base equals the number on the other side, the base to the number on the other side equals the input by rewriting it as a exponential expression. And then it depends on what's inside as to what type of equation you get, but you solve that equation for the variable and check and make sure you can completely check and make sure your answers are correct by plugging them in, but you definitely want to check and make sure that you can actually plug them in. Here's an example that actually creates an extraneous solution. So I have two logarithms being added. Log of x plus 15 equals 2. Okay. So I have to do that step 1. I have to isolate a single logarithm. So we have to use our rules from the previous section and multiply those inputs together. So the log of x plus the log of x plus 15 is equal to the log of, we multiply them, x times x plus 15 equals 2. Okay. So that's step 1. If you're looking at the guidelines, we've isolated a single logarithm. I'm going to go ahead and distribute. I get x squared plus 15x. And then I'm ready to get rid of the log, and you can either do 10 to both sides, so you'll get the inside equals 10 squared, or the base is 10 squared equals x squared plus 15x. That gives you a quadratic equation. I've seen a lot of people over the years on a problem like this get rid of the log and then get stuck. This is a quadratic equation. Set it equal to 0 and you can factor or use the quadratic formula. So 10 squared is 100, subtract that, and this one will actually factor with a 20 and a minus 5. 20 times negative 5 is negative 100. 20x minus 5x will give me 15x. Set each of those equal to 0, you get negative 20 and 5. 5 works just fine when you check it and plug it in, but negative 20 is actually extraneous. When you plug in negative 20, you have log of negative 20 and log of negative 5. You can't do that. Those are imaginary numbers. Negative numbers are not in the input, or in the domain of logarithms, so negative 20 is actually an extraneous answer, and the only answer is x equals 5. Okay. We created that extra answer when we multiplied the inputs. Remember, when we looked at the rules, it says we multiply the inputs if the original inputs are positive. So we actually created this extra answer when we created the x squared term. That's just part of the process, though. You solve the equation by the methods we have and then check and see if any of your answers have to be thrown out. Okay, one more example, this time with subtraction in the middle. So you have to combine the natural logs here. We've got subtraction, so we divide the inputs. We get natural log of x squared over x. You can cancel that. X squared over x is just x. So we have natural log of x equals 2. If you rewrite this one as an exponential, you're done. The base of natural log is e to the 2 equals x. E squared equals x. So our solution is x equals e squared. And that's in the domain of natural log because e squared is a positive number. So no extraneous solutions.